In today's video, we will consider an introduction to and some aspects of double integrals. Double integrals are, as expected, direct generalization of the definite integral to functions of two variables. Because of the similarity in the definition, which is more or less the same in all Riemann integrals, as we will see later, for example, triple integrals or line integrals, the basic idea is the same. So this brings a lot of similarities, but also there are many differences. So let us first recall the definite integral. Or rather, how we defined it. To start with, we had a function defined on a closed interval into R. Okay. And if this were not a bounded function, there would be no integral in the first place. So we can assume it's bounded, but it's a consequence of the existence anyway. And then the next step was to consider a partition. So we have the concept of a partition. So let P be a partition. This meant that a partition of AB, that is, A is x0, we had x1, and we had xn equal to b. So these were some increasing numbers in the interval with endpoints A and B. Now, and then, we considered the second concept was Riemann sums. These were actually threefold. There was a lower sum, there was an upper sum, and there was the general Riemann sum. I will consider all three of them. These were of the following sort. We considered the sum of the minimum of f of x when x was in xk minus 1xk times the length of the interval, and we considered the sum of f at any tk, but tk would be in the interval xk minus 1xk times xk minus xk minus 1. And the last one was the maximum of f of x when x was in xk minus 1 xk times xk minus xk minus 1. All of them were 1 to n. Now, since f of tk is a value between the minimum and the maximum values, obviously we have the inequalities this way. Now, this was called the lower upper, the Riemann sum. This was called the upper Riemann sum, and this was called a general Riemann sum. Just the way of showing them. Now, in this formulation, certainly the minimum and maximum values of f may not exist, even if f is bounded. but we are sure if f is continuous, they do exist. Okay. So I will not change my notation, but simply note that if minimum or maximum does not exist, one uses, okay, for the minimum, the greatest lower bound, okay, respectively, the least upper bound of f on the interval xk minus 1xk, and so on. So I will not change my notation, but this is the more general definition. When we look at this definition, actually we observe that we are not interested in the endpoints, xk minus 1 and xk, but rather, okay, we are interested in the interval. So x is in the interval, and this is the length of the interval. Okay, so we can represent a partition using intervals, actually. Well, this does not change anything in one variable, because an interval is exactly well known if you know two endpoints. So that is immediately there. Okay, so let me just say that we are interested, okay, in the interval. And, okay, length of this ik, if you call this the interval ik. Okay. So in the Riemann sum, we have the length, and the point is chosen from this interval. So actually, these are intervals, not just points in this sense. Okay. And then we said that we took a kind of a limit, and this limit was the following. We had the notion of a partition, which was the maximum of the lengths of IKs, where k ran from 1 to n. Okay. So this was the biggest interval length. And then we basically said, I will not cite the exact definition here, and then, okay, we said that if limit this mesh size approached 0, and we obtained the limit of UFP, and if it existed, and if it were equal to LFP, okay, hence, okay, limit SFPs, because they are between them, okay, is the same. Okay. Then we said that if this is true, then this common value is the integral, shown by sum, shown by this formulation. So this is the number which satisfies these limits. Okay. And then, of course, we had one more thing, that if f were positive, then we said that this was area of the region these are all familiar things, of course, given by this. Because f is positive, okay, this was the area of this region. Actually, you could take this as a definition here. Now, with all this structure, let us try to generalize this to the case of two variables. Namely, okay, now we have a function of two variables. Now what will happen? First of all, let us start, okay, from the partition. Well, before the partition, okay, we had an interval AB here. What will that be in the case of two variables? The domain consists of points in R2. So we have to generalize the interval. Well, the immediate and the logical generalization is a rectangle. So, okay, let R, say, be AB cross CD, meaning all xy's, so that x is between A and B, and y is between C and D. Of course, this is a subset of R2, okay, be a rectangle. And f from R2 real numbers be defined. Okay, so this settles the interval thing. Now let us take a partition. Now, what is a partition here? Well, because a rectangle consists of two intervals cross-producted, then we can do this in each interval separately. So, a partition P of R is the following. We have A and B here. We have C and D here. So this is our rectangle. This is our. Now we divide that into pieces. So we will call this x0 as usual, this xn, and we will divide this into some pieces. Well, here somewhere I will have xi minus 1 and xi. Okay. So I divided the interval AB into n pieces, n subintervals, that is. Do the same thing here. Okay. Let this be y0. At some point, I will have yj minus 1 here, and yj. And finally, I will have ym as my d. So I divided the interval CD into n pieces. Well, they don't have to be the same, n and m. Okay. So this gives me a rectangle which I will call the rectangle R sub ij. Okay. Of course, I exaggerated it. These will be much smaller because you will let these subdivision numbers go to infinity, the intervals will get smaller and smaller, and so on. But for the time being, okay, let us concentrate on this rectangle Rij. Note that I'm not very much interested in these numbers, but rather in the rectangle. So, this is now a partition of the rectangle R into smaller Rij's. Now, when I form a Riemann sum, okay, what will happen here? Well, as in the previous case, okay, we have, okay, three things to start with. Namely, I can talk about a sum of the minimum values. If minimum does not exist, we can again pass to the greatest lower bound version, but we will not consider that generality. You can assume f is continuous, for instance, to understand it better and make it simpler. The minimum of f of p, here p is xy, such that p is in the rectangle Rij. Well, Rij is a closed and bounded subset of R2, so if f is continuous, it will have a minimum. If not, take the greatest lower bound. And then we will multiply with, now, in analogy with the one-dimensional case, there we put the length of the interval. Well, now we have small rectangles. So we will multiply it with the area of the rectangle Rij. And then we will sum over all i's and j's. Well, there are two of them. So we can formulate it as I running from 1 to n, j running from 1 to m. Now, this considers all possible combinations. Okay. Now, somewhere at the middle, we will have, for an arbitrary choice, okay, this will be an element in Rij, and its arbitrary point, and we multiply again by the area of Rij. And of course, it will be smaller than the maximum value taken. As before, we will call this, now it's a Riemann sum, but modified to two variables, the lower Riemann sum. Okay, I use P in many meanings, but it's understood. This P is the point xy, but this is now the partition P. This will be denoted by SFP, and this will be denoted by UFP. So these are the Riemann sums that we consider. Well, next we have a mesh size of the partition. Okay. The basic idea is that the intervals in one variable get smaller and smaller. Well, it's equivalent to say that their lengths get smaller. When the length of an interval gets smaller and smaller and goes to 0, it means the intervals themselves shrink towards one point because their lengths are smaller and smaller. Now we want the same thing in the case of two variables. So how can you make a rectangle get smaller and smaller? Well, both of its sides must get smaller. But you have two things here. Well, you want the area to get smaller, but a rectangle can be very long and thin, and the area can be small. So to guarantee everything, that is, the area goes to 0 and the rectangles shrink to a single point eventually, a clever way is to look at, instead of two sides, look at the diagonal. The diagonal length in the rectangle, if it goes to 0, all of these things go to 0. So this will be defined as the maximum of the length of the diagonal of rectangle Rij. Of course, what is this? Remember, Rij was from the picture up there, okay? Xi minus xi minus 1 is one side. And yj minus yj minus 1 is the other side. To calculate the diagonal, well, actually, it's the length of the diagonal. So it will be this one. So over all i's and j's, okay, these diagonals will be smaller and smaller. Eventually, we will pass to the limit. Okay. Now, with all this preparation, okay, then we can now formulate the integral. Namely, okay, this is the tentative definition. Okay. If limit partition length, that is the lengths, the maximum length of the diagonals, goes to 0. If you have UFP and the limit partition length goes to 0, LFP are equal, then this common value is called the double integral. Of f on f. Okay. Shown by? Well, these Riemann sums are double sums. You have two sigmas there. So that's why we show it by this. Note that instead of dx, now we have dA, meaning the area. Okay. So we multiply values of f by the area of Rij's. Okay. So this is the tentative definition. The formal definition, we will have two versions there. So let me just state that over here. Well, the first one is over a rectangle. That is, okay, R is a rectangle. Okay. Then, okay, if there exists some number, a real number, such that, okay, for every epsilon, there is a delta such that, okay, now we are making the limit over there more precise in this formal definition, even though we will not use it, okay, just for the sake of completeness, such that, okay, for every partition P with the mesh size less than delta, and for all choices of Pij stars in Rij's. Of course, here I assume that this partition is actually Rij's. Okay? One has the Riemann sum SFP, that is the sum I1 to n, J1 to m, F Pij star times the area of Rij minus I is less than epsilon. Then we say I is the double integral value. Of F on R, and shown by as before by this. So this is the formal definition. It just explains the tentative definition in more detail. Now, what is the second definition? Well, in real numbers, you have intervals, and that's all you have. But in plane, you don't always have rectangles. For example, if we want to evaluate a double integral over not a rectangle, but a circle, a disk, well, that doesn't fit into the first definition. So, if D in R2 is bounded and F is defined and bounded, then let f hat xy be fxy if the point is in D and 0 otherwise. Okay. Now, for any rectangle R such that D is contained in this R. Now, obviously, D is a bounded set, so you can put it in a rectangle. It's not important which rectangle you put it in. Okay? Well, this needs proof, of course, but we will not do that. One defines the integral over D of fxy dA is the integral over R of f hat of xy dA. Now, the right side was already defined because this is a rectangle. So we now make the new definition. On any D, you can define it this way. Of course, if the right side integral exists, it's a limit, then this one will exist, and that's the definition of a double integral over D. Okay. Well, before we move further, okay, let us have the existence theorem. Well, if D is closed and bounded, and F is defined and continuous on D, then the integral exists. So this is a direct generalization of the existence theorem in one variable, but be careful here that D is not an arbitrary set. Okay. Even if F is very nice, okay, D may not exist. I mean, the integral on D may not exist. Okay. Actually, this is still not exactly correct. You need a little bit more than closed and bounded. You need some kind of regularity, okay, which I will not go into that, okay. Maybe I should just say, well, and, okay, nice set. Okay. What I mean by that will not be clear now. It is beyond our scope, so I will not go into that. But closed and bounded regular sets like circles and rectangles or half circles, all of them will be all right in this setting. Okay. Now an example. Let our function be x squared plus y squared. A polynomial, so continuous, everything is fine. And let R be the set of the rectangle with 0, 2, cross 3, 5. Okay. That is to say, we have the following. Okay. Let's say this is 1, this is 2. I said 0 to 2. Yes, this is my x. And on the other side, I have 3. So I'm not making it very proportional. I have 4 and I have 5. Okay. So I get this. The rectangle is 0, 2, cross 3, 5. So it is this. This is my R. Okay. Now, on this, okay, with the partition, P, where you divide them by 2 all the time, that is, okay, P is, well, how should I show it? Well, yes, directly. Okay, P such that, okay, n equal to 2, m equal to 2, with equal lengths. Now, this means that we divide, okay, this into 2 pieces of equal lengths. So I have 4 of them. In other words, I have here R11, okay, here R21, R12, R22. Here I is 2, so I'm in this interval. But J is 1, so I'm in this part. So I get the rectangle R21. Okay. So the question is, find, okay, LFP and UFP. Now here, clearly, the area of Rij is always 1. In whichever part you are. All of them are squares, actually, with side 1. So the areas are easy. Now for the lower Riemann sum, I need the minimum values of f on each of these 4 pieces. Okay. Now, the minimum value or values of f occur, okay, at the point in the subinterval, for example, in R11. Okay. It will occur on the smallest x value and the smallest y value, which means the left lower corner. And the maximum values will occur at the right upper corners. Okay. So, with this observation, well, that's obvious because you add the squares. Okay, so if you take the biggest x value and the biggest y value possible on the subrectangle, you get the biggest value of the function. You add them together. So let us make a table. Okay. Let us calculate the minimum of f and the maximum of f when we are in R11, in R12, in R21, and in R22. For simplicity of calculation. Now, in R11, here, okay, the minimum value occurs at the point 0, 3. Because it's the lower left corner. In R12, it occurs at 0, 4. And at R21, it occurs at 1, 3. And at R22, it occurs at 1, 4. Okay. These are the f values. Now the maximum values, well, for the R11, it's at 1, 4. Of course, it's square, but fine. In R12, it occurs at 1, 5. For R21, it occurs at 2, 4. And finally, for R22, at 2, 5. So, okay, LFP will be 1 times, this is the area, they're all equal to 1. I'm taking it out. The sum of these values. So it is 9 plus 16 plus 10 plus 70. Okay. So this happens to be 52. And the upper sum is 1 times, these are the areas, they're all equal, so I will not put that. You take the biggest values, so it is 17 plus 26 plus 16, 20 plus 25 and 4, 29. Okay. It happens to be 92. Am I correct? Let me check. Yes, it happens to be 92. So these are the upper and lower sums for this partition. Okay. Well, this, of course, says that, okay, the limit of the upper partitions and the limit of the lower partitions, I did not explain that, but again, as in the case of one variable, when p gets in mesh size smaller and smaller, the upper sums get smaller, the lower sums get bigger. They meet at one point in the limit, and this is the integral. So, okay, the integral is between these two values. Okay. Actually, it is not difficult to calculate, 70 and 2/3. Very near 71. Okay.